Sorry?
Where does the electron begin? By that
blackboard? Let me label. Okay, so let me probably start. So this is blackboard number 1, and that is number 2, and this is number 3. And this is number 4. It's all in my note, updated last night. So let me clarify certain issue. This come from, thank you so much for question. It's always good. I feel like I didn't answer some of the question in a satisfactory way when I talked to you. And I think I decided this example should answer your question, okay? It's in my note right now, so feel free to open the Dropbox link again and then you will see, okay? So let me explain certain things. Can you hear me? So basically, yesterday there were questions about the relations between A maximization and the A theorem. So some of you asked me this question. I think it's really nice. Okay, so I decided to spell out explicitly. So let's do one example. SU2 SQCD with 4 flavor, 0 superpotential. This is electric theory, okay? It's in a conformal window. So conformal, fine. They flow to a superconformal point. In the UV, because we don't have interaction, gauge coupling is weak. So this is a free CFT. So we can assign our charge to be 2/3, okay? And then we can compute this A coefficient, the A and the conformal anomaly AUV. And you see that if you plug this 2/3 in, it's just 16. Why 16? Because we have quarks, 8 of them, 2 times 4, and antiquark 2 times 4. So they're 8 plus 8, 16. Free chiral. 3 free vector. Why 3? Because we have SU2. SU2 has dimension 3. So when you add up, you get this number. This is approximately 0.9. This is, you use the value of the free CFT to feed in. In the IR, on the other hand, you know that there is superconformal R charge. This theory flows to a superconformal symmetry, superconformal field theory. So, and you know that we did this before, this 1/2. So you can compute this thing and plug it in. But observe here that even though we compute things at the CFT, strongly coupled CFT point, we use weakly coupled description because we still use the fact that there is 16 quarks, right? And SU2. This is weakly coupled description, but what we feed in is the R charge at the IR. Does this clarify? And we managed to do this because Toft anomaly. If not because Toft anomaly, we cannot use the weakly coupled description in the UV to feed this expression in. We compute this theory in the IR. This is strongly coupled fixed point, okay? Usually, not necessary that we always have luxury of having a description in the UV. But okay, in this case we have. So we just plug in. But we have to use the superconformal value. But then you get 0.75. And you observe that AUV is greater than AIR, as you expect. Okay, so this should clarify your question.
Is the reason that they are different that when we maximize the R star of the IR is different from the R of the UV?
Because it's 2 different CFT. Yeah.
Even though there is anomaly matching, so for a given R it matches with the IR, but they are
Yeah, suppose that you see, this is the thing about Toft anomaly because it allows you to use weakly coupled description to compute things in the strongly coupled regime. Okay? So this should clarify some of your question, I hope. Okay? Now, some of you asked me about intuition of the A maximization. Whether I suppose that you know that A theorem, back in the time when Interrogator and Vec developed this technique, the A theorem was still a conjecture. It's proven in 2011, so almost 11 years later. So, okay, so whether there's intuition, yesterday I said, well, if you look at the proof, it's highly non-trivial. There's some kind of intuition you can develop, but this intuition have loophole, so you have to be careful. Okay? So, A maximization intuitively implies the A theorem, at least for some SUSY theory. You have to use it in a careful way. If you consider an RG flow from a CFT, which I call CFT UV, to a CFT IR, which is basically in this example. You start from a free CFT, you flow, then, okay, often, but not always, okay, this is important. The flavor symmetry in the IR is a subgroup of the flavor symmetry in the UV. Why? Because you have to turn on some relevant deformation. Okay? In this case, it becomes like, for example, this flows trigger, and you have to have some relevant deformation to flows. Usually, this relevant deformation break flavor symmetry. Okay? However, okay, now suppose you assume that this is true, then you observe that you maximize over a subset of a smaller one. This usually leads to a smaller number, right? Because in the IR is a subset of the UV, so you remember you have to maximize over S. And if you maximize over smaller number, you get a smaller A. So this is intuition. I don't know you like it personally. At 2019, okay, fine, it's good to have this intuition, but now we have proof for A theorem, we have proof for A maximization. They are both good, okay? But warning that I would like to give you here is it's very important. That there are a lot of examples, and by now we have a large class of them, that FIR is not a subgroup of FUV, okay? This phenomenon is called accidental symmetry. It can happen that you flow and there is some symmetry that emerge in the infrared, but not in the ultra. We will do one example here actually. At the end of this lecture, I will give you a theory called Mariyoshi song. So this theory has an accidental symmetry. Like as you will see, I explain why it's happened. Okay. So this is a loophole of the above argument. But if you want intuition, this is the intuition. This is written in the original paper, by the way, of interrogator VIII. Okay. So, is there any question about this? If not, I will proceed with an example now. Okay. So let's do. Last time we maximized a very trivial theory, namely a free chiral. You remember, and we get 2/3. Okay. Let's do something a bit more non-trivial and see a far-reaching consequence of the A maximization. It's really deep, this thing. Okay? So this model is very new, actually. I take it from reference 45. This is to Rasamat, Shlomo Rasamat, Zella, and Gabi Safria. This is only 2017, the end of 2017. So it's a very new example. And I'll tell you why these examples are quite rare, actually. So let me erase the first blackboard. Okay. This example is an example where you have enhancement of a global symmetry in the infrared. A model, this is example. A model with the enhanced E6 flavor symmetry. Okay, I cannot explain everything to you because we need more tools, but you can see some gist of E6 from my explanation. This is 4-dimensional model with n equal to 1. It's known that it's super rare to find some example of this type that enhance a lot, but by now we have a collection of them. If you search for paper of Shlomo Rasamat lately, it's all about, mostly about the enhancement of a global symmetry to a very nice one, actually. Yeah. So this is a very nice example because consider a theory with an SU2 gauge group. So it has only one gauge group. This is why it's very simple and nice, and it's good for teaching. 8 fundamental chiral multiplet, okay, and a collection of singlet. Of each singlet. Okay, I will tell you more detail. So split. So this basically just what I'm saying is that you have SU gauge group, basically what we call 4 flavor. Okay. So it has Q in 4 and Q tilde, if you want to think in that way. Okay. So it has 8 fundamental, but now I will add a lot of singlet. But the trick is the following: we split 8 chiral fields into 6 chiral field QA and 2 chiral field QB. Okay, and couple them to singlets MA and MB. As follows. Okay, so this is I will start by doing this. So if you want, the theory look like this. So you have SU2 gauge node. Okay, I use this notation, the same notation as how you have seen. There is 6 here, and there is this QA, if you want. There is 2 here. You split 8 into 6 and 2. Okay. You can put arrow as you want here because SU2 has a very special property that 2, the fundamental representation is pseudo-real. 2 and 2 bar are the same. So it doesn't matter, it's going out or going in. Okay. Let's call this QB. Okay. Then I introduce a singlet using cross MA and MB. Okay. So these MA and MB, the superpotential is as follows. It's E epsilon alpha beta. This is the gauge index. Okay. Contracting MA IJ QA I alpha QB QA J beta plus epsilon alpha beta MB UV, okay, QB alpha U QB beta V. Okay, so let me tell you, alpha beta equal to 1 to 2. These are SU2 gauge indices, okay? IJK will run from 1 to 6, okay? These are SU6 flavor indices. And I will use UVW from 1 to 2. These are SU2 flavor indices, okay? So is it clear, the notation? SU2 gauge has epsilon tensor. So this is why you can contract them like this, okay? So now if you look at this superpotential, you see that MA, so let me write it down. So MA, you can think of MA as is a 6 by 6 anti-symmetric matrix Can you tell me how many independent components there are? 15, yes. 15 independent components. MB is the 2 by 2 anti-symmetric matrix. So it has one independent component, okay? Right. So now some of you might, if you read recent paper, some people call MA and MB flipping field, but okay, we don't have to know the name for now. Okay, so what is this theory? So can anyone tell me what the global symmetry in this theory is? SU6 times SU2, okay? There's R symmetry. Is that all? Okay, if I split, forget about MA and MB for now. If I have two SU2 with 4 and 4, you would have SU4, SU4, and you have baryonic symmetry, right? There's a U1 also. But you have to make sure that this U1 is non-anomalous. In the SQCD, we call it baryonic symmetry, right? Here, I will show you that there's also one that non-anomalous, except that the computation is, can be done in a neat way in here, okay? It's the same computation that you can do also, okay? So let me proceed with this. So obviously from this diagram you see SU6 times SU2, and there should be U1R. So, okay, so let's consider the following. So let me proceed. This is the description of my theory. I hope it's clear, okay? When I write down this diagram, I tell you all the field component, I tell you superpotential, I fix the Lagrangian for you, okay? So instead of writing Lagrangian with all the component, d4 theta, d2 theta, I write it in this form, okay? Okay, let the trial are charges of the chiral field. That's the point. If you said it's U6 times U2, there are two U1. You agree? You can write it as U6 times SU2 is 2 U1. But I will show you that there's only one that is non-anomalous soon. Yeah. So you remember that we have to write R trial equal to R0 plus, just to remind you, this equation. You remember this equation. R0 you can pick to be anything. And then you mix with the flavor symmetry, right? With the mixing coefficient SI, again, is this undetermined. So it's your choice to choose R0, okay? Which choice should I choose? There is a clever choice, which is more meaningful than the other. Of course, you can choose to be 0. This is also nice, but it's not so meaningful. The meaningful one is to choose to be 2/3. You assume that every field are free, then the mixing of a flavor symmetry make it become non-trivial value. You see what I mean? So I will pick the R charge, but you can do it any choice as you like. But this choice has some significance. I will tell you why, okay? So RQA, I will choose to be 2/3 plus X. So what is this X? So I choose to mix, this is the mixing coefficient basically, with the coefficient, with Fi1. So this, if you want, is a U1QA. Okay? So this mix with the 2/3, which is the free value. I can also choose my QB to be 2/3 plus Y. Okay? Again, this Y is the mixing coefficient here with charge 1. Okay? So I choose R0 to be 2/3, and this is the charge 1. Mixing coefficient is Y. So if you want, this is U1QB. Now there are two of them, right? As you want. Now R of MA is fixed by superpotential. You cannot choose it otherwise. Because superpotential has to have R charge 2. So this is 2 minus RQA minus twice RQA, right? So this would be 2 over 3 minus 2x. This is not free anymore because you have to choose such that superpotential has R charge 2. Again, the same thing as RMB. Let me write it here. RMB, this is 2 minus 2 RQB, which is 2/3 minus 2y. Okay? So now I assume that there are two U1. The mixing coefficient is called x and y. Okay? Now the thing is that what shall we proceed next? We want to see if this admits some solution, right? For the non-anomalous R symmetry. So at the moment, I haven't done anything about R charge, if you observe. I haven't mentioned R charge at all because I don't know what the superconformal values is or whatever. I mean, but now I'm going to do. So I want to write down the condition for the non-anomalous symmetry, which is basically the zero beta function. Okay? Again, this I have shown. 0 equals T times adjoint. There's one gauge group, so you can do SU2 gauge group, right? Plus sum IT Ri in representation with the R charge minus 1. You remember this formula? Okay, this is from Gaugino, and this is from all the Cairo. You remember this? Let me remind you if you forget it. Or this is zero beta function, zero NSVC beta function. So let's plug it in. T adjoint is 2 because you have SU2 group. Okay, you use this for SU2 gauge group. Then, okay, what's the next term? Can you help me? 1/2, that's right. This is fundamental representation. So there are 6 of them, right? So let's do from this guy, okay? There are 6 of them that charge under this. So you have R of QA minus 1. This you agree? Then there is 2, because you have 2 of them charge under this, 1/2 RQB minus 1. Why MA and MB doesn't enter? Because they're singlet, okay? They're not charged under gauge symmetry. So this we do for SU2 group, okay? SU2 gauge. Okay? If you like, this is gauge R, triangle diagram, okay? So now you see this equation, when you plug these trial value in, how many you have left? Between x and y, you have only one left, and that's the non-anomalous one. This implies y equal to minus 3x minus 2 over 3. Okay? So we use NSVC beta function or non-anomalous R charge condition, and then it tells you that instead of having 2 of them, you fix with one unknown now. Okay? So good. So let me write everything in terms of x now, okay? So now RQA will be x plus 2/3. RQB will be minus 3x. RMA will be minus 2x plus 2/3. And RMB will be 6x plus 2. Okay? Right. So now, look at this equation. So instead of have 2 U1, which can mix. You have one of them now that can mix with the original R symmetry, right? And the mixing coefficient now is called X. Okay? What's the magic here? The point is that now the coefficient of X will give you the value of non-anomalous R symmetry automatically for you. Right? Because this is the mixing coefficient, so you can just recharge in front of X basically. It's so simple. Okay, so let's read it off. So let me erase this blackboard and tabulate things for you. So this implies that there is a non-anomalous U1 non-R flavor symmetry. I don't know how to call it. Some people call non-R symmetry flavor symmetry automatically. Think of it as baryonic symmetry, roughly like that, okay? Yeah, it's confusing because even the magnetic symmetry in 3D sometimes, because it's not part of R symmetry, some people regard all of that thing as a flavor symmetry somehow in a fixed point, because at superconformal field theory, there's no gauge field to talk about. You can call symmetry, which is non-R, flavor symmetry. This is the terminology, so don't get confused. Maybe I dropped non-R symmetry. Okay, which we call U1H, okay? The charges of the chiral field under U1H can be read off from the coefficient of X in let's call it dagger. Okay? So let me tabulate what I can tabulate for you. Okay, so at the moment, so far we have the following. Okay, so this is SU2 gauge. At the back, can you see this? It's a bit small, right? Yeah, okay. Maybe, okay. There's not too many symmetry. Gauge. And then there is SU2B, SU6A, and U1H. In fact, there should be another column which called U1R, right? But we do it later. U1R. Okay? So now there are 4 fields only. QB, MB, and MA. Okay? So, okay, let's help me to fill in each element. So QA, look at the diagram, is in 2. Right? Doublet of SU2. Under B, it's a singlet. How do you write boldface on the blackboard? I'm really bad at it. Okay, so, but you know what I mean. It's and SU6 is going out, so it's a fundamental. So it's 6. And U1H, the charge can be read off from the coefficient. Let me normalize it like in the same original paper. Half of the coefficient. The authors choose to normalize it by 1/2, but this doesn't matter for me. I can choose to be original value. So in A is 1/2, don't know why, okay. So we can do this. Okay, QB give two singlet, and you see that it carry charge QB, so you have minus 3/2. I cannot fill in U1R. Okay, let's make it R star, okay? I want this to be the R star, but I don't know the value at the moment. We'll check it, we'll do it later. So now MB is 1, 1, 1, 3, okay? 1, 1, 15 bar, and minus 1. Do you agree with these values? This is what I can fill in at the moment, okay? Right, next we'll compute U1R star. Say again, please. No, there are one independent component. Yeah, they're single. It's true that it's anti-symmetric, so it's a singlet. Okay, now get the, now can you guess what I'm going to do next? A maximization, of course. So let's compute trace R cube. Okay, so our A will be A trial, 3 over 32, 3 trace R cube minus trace R. Okay, this should be the trial value, and this. Sorry that I don't write T everywhere, just to not clutter the notation, but you know what I mean, okay? This is going to be a trial value, okay? Which are these. So let's compute trace R cube. Okay, now we have this table of charge. It's really easy for our life now to read it all, right? So you have 12 RQA minus 1 cube. You understand why it's 12? Because 6 times 2, right? It's 12. Plus, now let's do the B. How many? 4. So 4 RQB minus 1 cube plus, next, let's do MA. So 6, 15, there are 15 of them. RMA minus 1 cube plus RMB, there are 1 of them. So 1 times RMB minus 1 cube plus, what else? Gaugino, exactly, thank you. So how many of them? 3? Yes, because you are in SU2 gauge group, Gaugino has R charge 1 cube. Okay? Then feel free to plug dagger into here. I won't write it, okay? Now, trace R is similar. You just drop the cube in every term, right? Yeah. So please do it yourself, okay? I write it in the note. I just, with LaTeX, it's easy. You copy and paste, and you erase the power 3. Okay, so trace R is a similar thing. Just drop the cube power, okay? So now if you evaluate this, let me tell you, you can use Mathematica to do it or whatever your favorite method. It will be 81 over 4 x squared minus 9 over 2x plus 9 over 16. Okay? Okay. And this reaches the maximum at x equal to minus 1 over 9. Okay?
Generally, expect this to be cubic.
Oh, now, good point. This, good point. The point is that I don't know whether I write derivative of a with respect to x or x. Let me check. Good point. Let me see. A maximization. Okay. Oh, this turned out to be quadratic here. It's fine. Yeah. Here, global maximum. Yes, in this case, yes. But what we interest is the local maximum, okay, which is fine. So. It's what?
Is this relevant somehow?
No. In this case, no. It's fine. In general, you would expect the cubic guy, okay? But in this case, it happened that our computation reduced it to quadratic. It's not a problem for me.
So that's not this example special.
No, it's not something failure. It's just the fact that you have to test that second derivative is negative. It's which is, I think it's fine. Okay. Yeah, second derivative is to be 81/2. Okay, so, right. So, well, we are fine with this. So now let me erase this. I can also explain another thing for you, that once you do this example, because of the quadraticity, it's turned out that this is have some special value, which is turned out to be rational number. In general, you can have algebraic number. No one tells you that this is so special in this case, but this case is special. But it's still mixed, as you will see, okay? So, indeed, you will see that from the equation dagger, x is non-trivial, right? So you have a non-trivial mixing still with these guys. So if you compute A and C, it turned out that, let me erase this blackboard. I invite you to do this example yourself. It's easy mathematical writing, right? One line and it's algebraic equation, very, very simple. It's very instructive. You should do it once in your life. And that's it. And at which the conformal anomalies are A over C, A and C being very nice number. Okay. So now we can tabulate this, complete this table. It turned out this to be 5/9. If you plug the value of x into those equations, you will get 5/9, 1/3, 4/3, and 8/9. Okay? Good. Okay. Next, we want to look at the certain operator. Now, again, to have a meaningful, we have to talk about gauge invariant combination. Okay? So let's take the smallest one. Among this table, this is 3, 9, but this is not gauge invariant, you observe? This is gauge invariant, so this is smallest one you can think of, right? So, MA. So look at the lowest gauge invariant object that you can tell me. Okay, there was this guy as a candidate. What else you can combine as a gauge invariant for me? Lowest R charge, lowest R star charge. This one, okay? This is 12/9, so it's not the lowest. So this one in the 15 bar of A, okay? Can you find another one for me, which has precisely 8 over 9. QA, QB, exactly. Okay? So, the operator with R charge, let me be strict, R star charge, okay? 8 over 9. Okay, let me emphasize gauge invariant. Operator, which R come from MA, right? And QA, QB. How do you contract the index? Right, so basically QA, let me be consistent with my previous notation. QA has I alpha, okay, you agree? QB has alpha up and U down, right? You contract the alpha, so it's gauge invariant. You agree? I run from, again, 1 to 6. You run from 1 to 2. And MA is in the 15 bar of A, okay? Right.
Why couldn't we have QB, QB with the
QB would be 2/3, right? But QB, if you do it, it's 0. Right. So QA, QB is the lowest guy, okay, that you can do. This is the 8 over 9, okay? Excellent. So now you have MA in the 15 bar of A. This guy turned out to be 6 in the A and 2 in the B. You agree? Okay. So how many if you add up? 27. Do you recognize this number? What's the fundamental representation of E6? 26, 27. Yes. So this is actually the 27 bar of E6. Okay? So you might be surprised what I'm doing here. Is it really true to all order? And this is are you lying to me or anything like that? No. So first of all, let me show you. 27 bar, you can do the branching rule. There is a art program or a paper by Yamatsu. You can look at those. This is an encyclopedia of the group representation. So you can do the branching rule of E6 goes to SU6A times SU2B times U1H. And if you look at the 27 bar of the E6, it goes to 15 bar times 1 plus 6, 2, and with this normalization of, with this thing, okay? I think you can put -1 in both. This is, look at the AMMA charge, this is -1. And QA, QB add up to -1, right? So this is carry charge -1 under the U1. All of these carry -1 under the U1H, okay? Is it clear for you? If they don't have equal H charge, you're in trouble. Can you see why? Because if they don't have equal H charge, you cannot combine according to this branching rule. It breaks the multiplet of E6, right? And now you understand why it's so important to A maximize thing. There are twofold. the condition of a non-anomalous R charge give you non-anomalous U1H for you, which turn out to be so accidental that these two guys combine. Secondly, the R charge that you obtain from maximization precisely make these two guys combine also. Right? This is one of the power. Now, if you don't trust me because I just do two operator, come on, I mean, this is too little. You can compute supersymmetric index on S3 times S1. Too bad, I have no time to do this. But if you do it, which I have it in my note, equation 1033, this is the full expression. Feed it in Mathematica, expand in 1036 really. You will see the current, conserved current of 78, which is a joint of E6 appearing. Look at T squared term in the note, 1036. This is a very strong confirmation of the existence of the enhancement of the E6 symmetry. You can proceed to higher order. You can always see the E6 representation appearing as a coefficient, okay? So this is another power of a supersymmetric index. Unfortunately, I have no time to do it. But you get the idea. I did one operator for you, okay? So let me emphasize again. These E6 enhancement come from twofold. U1H has to have the same charge. If they're carrying different, you cannot combine into 27. And if U and R charge has to match such that they combine also. Okay? This is crucial. So, any question on this example?
So, in principle, you start with U6 times U2.
Yes.
And that's kind of 56.
No, you can. Because you can start from U6 times U2, but non-anomalous R symmetry tells you that the one of them, and has to be this one.
Yeah. And then that can fit inside.
Yeah, it can always. This is unique choice. Yeah. So, any value you choose, you will differ from me by normalization of H. But I guarantee to you, yeah, do it as a homework, parameterize it in different way from me if you don't like my parameterization. You will see that if you do correctly, these two guys have to have the same charge. This is universal. If you pick the right non-anomalous, you want H, what I would call H prime symmetry, you will have to have this thing. It might be that you normalize it different from me, but that's fine, okay? Secondly, the R star, as I show you, is unique. So there's no movement you can do here, okay? So is it clear for you? Right, this is a very solid example and very simple to do on the blackboard because there's one gauge group. The other theory that I know of has many gauge groups, a complicated matter field. So it's impossible to do in a finite time on the blackboard. This is one of the simplest model. Okay? Good. Now, let's move on to the, if you don't have any question, let me move on to the final topic. And this is even more exciting. So I tied it with a caution, final caution. As I told you, when I said A maximization, field theory is a very hard subject, as you probably know by now. It's come with all the subtleties and this kind of thing. Indeed, A maximization also one of those. There is a caution on accidental symmetry, okay? So this, I already give you warning at the beginning of the lecture, but now let me give you explicit example. So we finished with the E6 example. Now you can come back and ask me why this theory doesn't have this subtlety. I guarantee to you know. So the subtlety usually come from the following. So I name a section, a caution on accidental symmetry. I think you have seen in Sohan lecture in 3 dimensions. Well, in three dimensions, emergent symmetry and so on are really, really common. It's very easy to come up, especially if you allow me to go into supersymmetric regime. In 3 dimensions, enhancement of a global symmetry is like, it's very easy to come up. In 4 dimensions, on the other hand, it's so rare. It's very hard to engineer theory that have enhanced global symmetry. So this is one achievement. Now, Okay, one must maximize a trial over the complete space of all possible trial symmetries, including all accidental symmetry. So this is come to the hard part. How do we know? Okay, we have only one situation. Now you can ask me very difficult question. Is this classified? Let me give you what I know, okay? Where accidental symmetry are readily apparent and required. You see that I'm really careful here because this is the case where we know what to do. In the other case where the accidental symmetry is not necessary that we have a prescription to deal with, okay? Is when a gauge invariant chiral primary operator from such as the meson, for example, hits or appear to violate the unitarity bound. R of M. If this condition is violated, then we call this violate unitarity bound. You will see that usually this can happen in the sense that if you're not careful, you do a maximization using trial R charge in a usual way, you see sometimes that there is some operator which R turn out to be less than 2/3. And that's where you get into trouble. Okay? So why? If it falls below unitarity bound, it means that, okay, you haven't taken all the symmetry into account. The interpretation is usually is that M then becomes a free field with an accidental symmetry. Let's call it J of M, under which only M is charged. Okay? This is a free field. Okay? So what happened? So you have to, the R trial, the trial RT must then include mixing with J of M. So basically you have to do R trial in the new in terms of R trial of O plus SM JM. Okay, you have to add the contribution to these guys into that. Yeah. With SM fixed by maximizing a trial. Okay? Okay. This leads to an additive correction to quantity, to the quantity a trial to be maximized with respect to other parameter Si. Okay, basically what I'm saying is that you have to redo maximization with respect to this new guy. Okay. This sounds very complicated to you, but there is a very simple way of fixing all of this. I will show you in an explicit example. It's more modern development of how people deal with this. In a modern example, I guarantee to you the richness coming from all of these guys. Okay? So now, this look abstract to you. Of course, this I will not leave it like this. I'm doing physics, so I have to show you explicitly what I'm doing. So let me do the last example on this thing. This example is called Enhancement of Supersymmetry from 4D n equal to 1 to 4D n equal to 2 in the IR. This is a really new development. It's a really nice example. It provides you to have access to some CFT with n equal to 2, which believed to have no Lagrangian for a long time. Okay? This comes in the name of Mariyoshi Song type theory. Okay? Okay, this example I take from reference 46. I think this probably by now a few years ago, 1607. So, but the approach I'm going to use is CISA approach, which comes from Benvenuti and Giacomelli, 2017. Okay, so from those who come from CISA, talk to them. Giacomelli already left, but this work was done when he was at ICTP. Okay, it's a very simple theory. So let's start by considering an n equal to 1 SU2 gauge theory with 2 chiral multiplet with 2 fundamental. So I will write down Q with 2 index, okay? A and I. A run from 1 to 2. This is the gauge index. And I run from 1 to 2. This is flavor index. Okay? This, or not only this, it have also a joint chiral multiplet. So it has QAI with this index, okay, and a joint chiral multiplet, which I will call phi. Okay? So let's first do it naively. So let's first take zero superpotential. You will see that for non-zero superpotential, the result will be nicer. But let's do zero superpotential. Okay, can you help me with the non-anomalous? Ooh, let's take a break because this is a computation we have to plow through. But it's a nice example. So let's take a break and come back and we continue with this example. Any question, I'm happy to answer. 10. Okay, so let's continue. So I'm cheating you by writing when you are taking a break, save time. So again, we proceed as before. We write down the non-anomalous symmetry condition. This is the trace of a joint, which is 2. You have 2 chiral, right? Because this is the doublet. In the fundamental representation, IQ minus 1, the charge of the Fermi partner, and you have 2 phi minus 1, y2, trace, this is the T of adjoint again, right? Okay, because phi is in the adjoint representation. Now, again, you parameterize Q and phi in the most general way, but I love my 2/3, so I will put 2/3 and plus x plus y. Again, this implies y in terms of x. Okay, again. And now you can compute trace I cube and trace r using this formula. Now it's cubic. Very good. So this is as general. Now there's no accident, okay? Okay, maximizing a trial gives x is really ugly number. As I told you, in general, this is an algebraic number. I cannot help you. It looks really ugly, I agree. And this leads to R phi. You can just plug it into this equation. Let's call it dagger. So you plug it in dagger, then you have R of phi equal to 111, 601 plus 3, which is approximately 0.25. And no, I copied it wrong. Really wrong. I apologize. This is test function. This is correct, yes. At x, also ugly number, doesn't help. Okay. This R of phi is 1/87, 1009. Is everything okay? This is 0.26. And then if you look at gauge invariant, one of the simplest things you can look at for this theory is trace phi square. Right? You agree this is gauge invariant? Phi is in the adjoint, so let u equal to trace phi square. Then R of u is approximately 0.52, right? Which is less than 2/3. This violates unitarity bound. Violating the okay. So So bad thing happen in life. Yes. So these guys become free field. So there are two ways to proceed. Okay. Other way is just to remove this guy from the A trial, then put this guy with the R chart 2/3 in, re-maximize the whole thing again. Okay, that's one approach. I'm going to use the more popular approach right now, which basically the same philosophy, except that instead of well, you see, you have extra information to parameterize. This extra information can cleverly input into a new field. So basically, a way to cure this problem, a way, this is not the way, okay, it's a way to cure this problem is to introduce new field FU. This is singlet, okay? Under gauge symmetry. So it doesn't carry any index basically. It's just a free field. It's just, no, sorry, not free field. It's just a field where there's no indices, up or down, or no neither flavor, no color, okay? Known as the flipping field. I'm very sorry about this name actually. Some people really hate it. I know my collaborator, someone prevented me even to write it in the paper. This name, I think credit should go to Tachikawa perhaps. He used it first, as far as I know, but this type of field is there. It's already in the literature for a long time. Except that it has not been used in this context, in this particular context. Maybe I'm wrong, but yeah, some of my collaborators really prevent me to use this name, but since some people use it, I'm gonna follow. Some people call it flipper, okay? Flipping field for U with the superpotential, very simple superpotential. You put this thing into the FU times U. Okay, can anyone tell me why this is beneficial? Because this is a singlet, you allow to take derivative of W with respect to FU. What happened? U equal to 0. You wipe U out basically from the problem. Okay? So okay. So the idea is that the F term dW with respect to F of U equal to 0 implies sets U to 0, and so there is no unitarity violation. All usual computation can be performed. By the way, this is really important. So putting new field in is basically to put new information into the theory. So you basically do the instead of dealing with the unitarity violating object, you deal with the other guys instead. And this other guy has a benefit of setting this the bad guy to 0. Okay? Is it clear?
And we don't give any dynamics to FU, right? I mean,
No, FU is dynamical field. It's the dynamical field. Dynamical field. Yes, this is highly important.
So here you keep the U because you could, it was the gauge invariant
Yeah. Yeah.
But how do you know it's the only field, the invariant gauge field that you can build that?
So basically, you build an object which carried extra charge, right? Because you remember that when it falls unitarity bound, you have to introduce new maximization, new S of this is what I call S of M, right? That multiply J of M. Basically, that data was in F of U. Okay. How do you know this process is correct? Because first of all, it set the unitarity violating operator out of your theory, and you replace it with a new guy.
Yeah, no, but my question is, how do you know that you can build another gauge invariant field that violates also unitarity bound? Because here you are building one.
Oh, if there are many, you have to flip all of them. That's why it's a complicated problem. You have to tabulate. Usually in research, you have to be careful. Tabulate all the gauge invariant down and check that all of them, if there is some of them is a unitarity violating, you have to do this process to all of them and add, for each of them, add a flipping field into superpotential. The benefit of this is that now U times the FU will have R charge 2 minus U, you see. So let me show you this. So basically R of FU will be 2 minus 2 of R phi, which is 2/3 minus 2y. Okay? Now you have to compute the whole thing again. Okay? So now you recompute trace R cubed again with the same object because you use the Lagrangian. And look at what appears here. This is the new guy. You agree with me? This is what I call S of M. Now it's hiding in the new guy, which is we call F of U. Okay? So now you can do the same thing. Trace of R, again, you delete the cube there, okay? This is a gaugino, just to remind you. Okay. Now plug the trial version back again. Oh, now what happened? R of phi. Okay. Can anyone tell me that does NSVC beta function change or not? By adding this extra flipping field. It's the same as before because this guy is singlet. It doesn't carry charge. T of the singlet is nothing. So it doesn't enter. So the previous NSVC beta function was still working. Okay? So the relation before between x and y was still fine. Okay? So you erase it perhaps? Let me see. This still hold. Okay? So let me okay? Because you just add a singlet field. So you can write y in terms of x using double dagger. Okay? Now, okay, redo the computation again. You will see that A trial 1/6/7 is 999 x cubed minus 837 x squared minus 5x plus 137. Okay, then you redo this maximization again. Okay, and instead of using u, now you should use fu. Okay, so so ugly. Right. So let me just finish it, just to tell you that x is equal to 1 over 111, 31 minus 2 over 601. This is maximization. And this leads to R of phi being 111, 601 plus 3, and which is approximately 0.25, and R of FU is 2 over 111, this number, which is approximately 1.50, which is greater now to 2/3. Okay? Now you should use FU. Okay, fine. This is good. Yes?
Is there any way in which one can write down the current associated to the enhanced symmetry?
Yes. Any symmetry has to have an associated current.
But is there a procedure in which one can do it?
Let me summarize it at the end. Yeah. Remind me if I forgot, remind me this question. This is a very good question, by the way. Yes. So, yeah. The E6 case, I re-explain it, but let's go along the flow. You might say, why come up with this ugly theory? This look really ugly number doesn't teach me anything. Yes, I just to tell you that, okay, this is one procedure. Now come the clever people. They say that, even though I have, okay, let me write it in words. This is, so the story ends here. So I start from a theory with zero superpotential, okay? I do a maximization. I found a unitarity violating object. I flip it, then I cure the theory. The theory still look ugly. Okay, it's not my fault. It's not anyone's fault. You just have bad luck. Sfigato. Okay. Now, a very interesting thing. Theory arises when we further introduce another flipping field f of m for the so I think I can, since this is so ugly, let me erase this ugly thing. Which one? I want to keep that. Here can you go? Flipping field for the meson, for the operator. M equal to epsilon ij, a alpha beta, q a I, q j b. You agree I can form this operator? I have two SU2. One is flavor, one is color. I contract both of them with the, these are singlet. And take W to be this one. So this is superpotential of this theory. Really simple. It's just two terms. Fu times U, Fm times M. And this has an enhanced supersymmetry. Okay? Although, let me emphasize, the introduction of f of m is not necessary from the perspective of the unitarity violation we will see that it leads to an interesting theory. Okay.
When you started with the theory with no superpotential,
Yeah.
then you have to, this Baryonic Symmetry bound, you introduce the FU, but then this is another theory, no? So
Yes, this is the point. So also because it's you can think of this the philosophy as the same, because if you think that U fall below unitarity bound, right? You did the original theory that you maximize is wrong, basically. You didn't take account all the charges to maximize. Because when you maximize, you have to maximize over all of them, including the accidental guy. Now, to cure this problem, you can do it traditional way, or you can do this way, by this introducing the new guy. You already the U, right? You agree with me? Because of the F term. But this new, you use this new thing to substitute the old one. So it's really a replacement with something above unitarity bound, which is also a singlet. So it's a same. It's just another way of doing it. You can redo the maximization by subtracting also. It's the same result. Okay. Now, okay. So this is not necessarily. It's not, I flipped this not because it violates unitarity bound. I flip it because something nice happened. And if someone asks me, how do you know? I don't know. This happened to be like this.
But since it doesn't violate the unitary bounding, doesn't that mean they will be a different theory?
Yes, now it's different theory. Okay, good. Now it's different theory. Okay. Yes, this is a completely new theory. It's not the same old theory that we need to do it, okay? Thank you. So I hope I don't confuse you about this. So can anyone tell me, is this equation still true? Yes, you can introduce million flipping field. It doesn't change because you keep adding singlet into the same guy. You're adding, well, you just have to solve the same equation basically. That's why I don't erase this. Okay, so good. Double dagger, still whole. Okay. Now you parameterize R of M, R of the flipping guy of the Q to be this one. Okay. So now I have so many fields, I cannot keep track of them anymore. So let's summarize. To summarize, you have R of Q, R of phi, R of Fm, and R of Fu become 2/3 plus 2x. This becomes 1/6 minus x. For x, this is 5/3 plus 2x. How many non-anomalous U1 non-R symmetry we have? 1. Yeah, and the coefficient, as usual, tell us what their charges are. Okay, so, yeah. So, there is a non-anomalous U1H symmetry under which the charges of a chiral field under U1H again can be read off from the coefficient of x. as usual, as before, okay? Now, let's do the A maximization. You will see that this is extremely nice. So, again, okay, I have time. So R cubed is still 3 R5 minus 1 cubed. Why 3? Because this is adjoint, right? Plus 4 R cubed minus 1 cubed. 4 because you have QIA. Okay? Now you have to add all the flipping field. R of the flipping of U, this is singlet, so coefficient is 1. R of the flipping of M, and then Gagino. Okay? Trace of R can be the same, you just drop the, again, this we did about million times now, and in be this nice value. Okay, cubic. So you solve it, maximum. Suddenly, it's a rational value. Look at the previous example compared to this one. And furthermore, if you plug this into this thing, you will see that R of phi, R of Q, this is important. So R of phi, R of Fm, R of Fu. 5 over 9, 2 over 9, 8 over 9, and 14 over 9. Okay? So our charts are rational number. Well, very nice. Okay, now I can erase this. We don't need this anymore. A and C is also very nice. A and C, if you compute using these charges, it will turn out to be 11 over 24 and 1/2. Okay, why this is important? This turned out to be a conformal anomaly precisely of a known 4D n equal to 2 theory. Okay. It's called the 4D n equal to 2, Argyres Douglas. Could you tell me, could you raise your hand? Have anyone heard of this type of theory before? Somehow, okay. I'm sorry, my course is not about 4D n equal to 2, otherwise I would love to do this in the detail. It's beautiful theory. But it's a conformal field theory which has no n equal to 2 marginal deformation. Okay? Meaning that you cannot write this theory using Lagrangian in n equal to 2 language. Okay? Using n equal to 2 of type H1 or A1, A3. Okay. So let me explain a little bit. So this is a very special value of this special conformal field theory that has 4D n equal to. It has, as I said, it has no marginal operator. So you cannot, you don't strong coupling theory. You don't have Lagrangian to describe it in n equal to 2 language. Okay? There's no weak coupling thing you can expand. But now, if we claim that this theory flows from n equal to 1, we start from Lagrangian with n equal to 1, clearly. superpotential is clearly n equal to 1. There's no more. It's a very simple matter. It flows to a conformal field theory with n equal to 2 supersymmetry. Meaning, now we have a so-called Lagrangian description in n equal to 1 language that flows to this theory which has n equal to 2. Okay, there is something I should tell you. This is not so easy to compute, given that I told you before that before this Lagrangian was not known. So, but Tachikawa, Shapir, and Aharoni Tachikawa managed to use very indirect method to compute A and C before that, actually. And it precisely matched this value that we obtained, just using A maximization and the flipping field. Okay? So this is one nice stuff. I can even tell you a bit more about this theory. That if you compute operator dimension, yeah.
Is the fact that the anomalies coincide sufficient to prove that this has to be the
No,
case?
not at all.
This is
It's not a proof. Yeah, it's a conjecture. So I can tell you more and more evidence as we go on, okay? So another one is, furthermore. So matching of the central charge was just matching of two numbers. So you say, oh, it's very weak. What are you telling me? So there are more match. Furthermore, the scaling dimension of Fm, Fu, and if you have the gauge invariant X operator Xij equal to Qia phi AB, Qbj are, so let me write it here. I will leave this board soon. So instead of using R charge, you compute dimension. These operator dimensions, these are gauge invariant quantities, so it's well defined. We are not using non-gauge invariant. Now you can compare these with the operator in the Argyros-Douglas theory, and it's matched perfectly. So this is the second piece of evidence. More numbers, as you can see. And observe that they're fractional, right? Have you heard that there is a theorem? This is probably by Professor Cecotti. And there is another paper, I remember, who showed that for n equal to 2 superconformal field theory, scaling dimension has always be a rational number. You someone not. So and this they're based on some assumption, but this is reasonable assumption, and I think there's a Cecotti and collaborator and the other one. I could check and give you reference, okay? But this is nice. Well, in n equal to 2, you have this operator which you can define. Since originally you don't have Lagrangian, this coming from Seiberg-Witten curve, basically. You look at particular point in the moduli space of a certain theory, and then you manage to obtain this operator. This is originally how it was done. Unfortunately, I have no time to explain to you more, but this match, okay? Right. So now come to, this match with these, the scaling dimension of the operators of the H1 Argyros-Douglas theory. Okay. So now you can ask me a deeper question. From the point of view of n equal to 1, how do you see this thing, that supersymmetry get enhanced? Luckily, we have encyclopedia of n equal to. This encyclopedia is done by 3 people. I think it's very nice. They classify all the superconformal multiplet in every conformal field, conformal field theory between 3 and 6 dimension in various supersymmetry. These 3 people are Intelligator, Cordova, and Dumitrescu. Okay? So what they do is that they classify, this include also, 4D n equal to 1 has been done before actually, it was done by Dolan and Osborne. But, okay, this is a large class. You see, it's quite systematic. And you will see certain thing that this theory has something called extra supersymmetry current. This is a very special type of current that you can interpret this as if you have this type of current, the theory has enhancement of supersymmetry. So basically, I can formulate in another way, but this current is a sufficient condition, basically, the existence of this, and you can show that this theory has such a current. Okay? Supersymmetric index would be a way to go. You can compute up to, in my notation, would be 7/3. Then you can see the extra SUSY conserved current. Okay, this is one way. Second way is that you can see that n equal to 2 stress tensor multiplet can be decomposed into n equal to 1. It contains 3 types. N equal to 1 stress tensor, flavor current, and extra SUSY current multiplet, and we have all of them. So this is another piece of evidence that the supersymmetry get enhanced. So to answer your question, indeed, whenever we have symmetry, we have to have current associated to it. In E6 case, we see that in the current, if you look at the current, meaning that you look at particular multiplet, the flavor symmetry multiplet, you don't just see the current of SU2 times SU6 times U1. Okay? That would add up to 39 because these are the dimension of the group. You see 78. So this is one thing that you see. It's very accidental that you have to flows to the infrared. R charge managed to combine with each other nicely. H charge is working out nicely, and these guys combine. So this is a very highly infrared effect. You can only see symmetry in my first example in the infrared. It's not there in the ultraviolet. Okay? Here also, in the ultraviolet, you can only see 4D n equal to 1 supersymmetry. But when upon renormalization group flow, because of this adjustment of the R charge, hence the dimension, they have something called extra supersymmetry conserved current, and then you have enhancement of the supersymmetry. So this would be another support. So you can check this explicitly that this type of current is there in the theory. This is in the paper of Mariyoshi Song. Okay, so you can have a look at that. Right, and that would be the end of my lecture. There was, before I end, I would like to say some certain stuff. The material that I skip is the supersymmetric index, okay? This is, of course, a very important object, and if you work on field theory, if you don't work on field theory, okay, you don't have to know it, perhaps, but if you work on field theory, by now, I highly recommend you to learn this subject properly, okay? Because one day you end up using it, I'm pretty sure. Yes, so it's in this in my note. There are a lot of lecture notes on this subject. One notable one, which is more advanced than this course for sure, is a lecture by Tachikawa. It's on archive, okay? Of course, some material here are overlapped. Many approach I take from him. I learn from, this is my collaborator, I learn from him a lot, so it's a valuable lecture. There are older lecture by Seiberg, Intelligator, Agiris, so please have a look at this, and if you want to know more about the subject, I also put a lot of reference there. Finally, since, okay, it's not your final lecture, but it's my final lecture, I would like to thank the organizer, Davide, Carlo, and the others. Well, 2 of you are in this room. You work really hard to make the school happen and run smoothly. I really appreciate it, so please give them applause.